February 14th, 1904, Chicago, Illinois. The bearing failure that nearly destroyed everything would echo through American construction sites for the next 50 years. On the Marshall Field's building site, Thomas Smith watched 127 cubic yards of defective concrete pour from his revolutionary mechanical mixer. Steam rose from the ruined foundation as contractors shook their heads and reached for their shovels. European engineers had been right all along. Machines could never replace the craftsman's touch in concrete work. The German consultants had declared mechanical mixing theoretically sound but practically impossible. Too many variables, too much precision required. Too much at stake to trust American machinery over proven hand-mixing methods perfected across centuries of European masonry tradition. But in that catastrophic moment, as Smith stared at his failed invention, he discovered something the European experts had never considered. The problem wasn't that machines couldn't mix concrete. The problem was that American engineers were building mixers like Europeans built theories, when they should have been building them like Americans built everything else. The morning sun cast long shadows across Chicago's construction sites in 1899 as Thomas Smith stepped through the maze of lumber stacks and stone piles surrounding the skeleton of what would become the city's newest office building. The sound that greeted him was the same rhythm he'd heard on every major construction project from Milwaukee to Detroit, the steady scraping of shovels against iron mixing boards, the grunt of laborers bent over concrete ingredients, the splash of water being added one bucket at a time. Smith pulled out his pocket watch. 6:47 in the morning, and James Keller's crew had already been mixing concrete for nearly an hour. The foreman stood with his sleeves rolled up, watching his men work with the practiced eye of someone who had spent 23 years perfecting the art of hand-mixed concrete. Each worker moved in a careful sequence, sand first, then Portland cement, then the precise amount of crushed stone. Finally, water added slowly while the mixture was turned and folded with long-handled hose. "Mr. Smith," Keller called out, wiping sweat from his forehead despite the cool morning air. "You're early for the show." Smith approached the mixing board where 3 workers were combining materials for their 5th batch of the day. The mathematics were simple but staggering. Chicago's building boom demanded 2,000 cubic yards of concrete daily. That meant 480 workers like these, working 16-hour shifts, mixing batch after batch by hand. The waste alone, concrete that dried too quickly, batches mixed too wet or too dry, material that never reached the proper consistency, averaged 40% of every job. "How long for this batch, James?" Smith asked, though he already knew the answer. 12 minutes if the boys keep their rhythm," Keller replied. 14 minutes if young Murphy there doesn't get his water timing right. The foreman pointed to a red-haired worker who was carefully ladling water into the mixture. "See how he's hesitating? That's what separates a good mixer from a poor one. You can't teach that kind of judgment to a machine." Smith nodded, but his mind was calculating. 12 minutes per batch, 8 batches per crew per day, 57 cents in labor costs per batch. The numbers that kept him awake at night were even more troubling. Concrete mixed by hand cost $8.50 per cubic yard, and the inconsistent quality limited building height to 6 stories maximum. Beyond that, the structural integrity became too unreliable for architects to trust. Across the construction site, Smith noticed a group of well-dressed men examining blueprints near the project supervisor's office. Their expensive suits and formal bearing marked them immediately as European engineering consultants, the type of technical experts that American construction companies increasingly relied upon for major projects. These men represented centuries of masonry tradition, theoretical knowledge refined through generations of European craftsmen who treated concrete mixing as both art and science. One of the consultants, a tall man with a gray beard and gold-rimmed spectacles, approached Keller's crew. Smith recognized him immediately, Professor Gustav Weiss, whose textbook on concrete construction was considered the definitive authority on the subject. Weiss watched the mixing process for several minutes, occasionally asking questions about cement ratios and curing times. "The fundamentals are sound," Weiss announced to his colleagues, speaking with the measured precision of someone accustomed to academic discourse. However, mechanical mixing remains theoretically sound but practically impossible. Proper concrete requires craftsmen's judgment, the ability to adjust for humidity, temperature variations, and material inconsistencies that no machine can replicate. Smith stepped closer, unable to resist joining the conversation. Professor Weiss, what if a machine could maintain more consistent mixing speeds and timing than human workers? Weiss turned toward Smith with the polite but slightly condescending smile reserved for well-meaning amateurs. Mr. Smith, isn't it? I've heard about your experiments in Milwaukee. The problem isn't mechanical consistency, it's the countless variables that experienced craftsmen compensate for instinctively. Watch Mr. Kelleher's crew. Notice how they adjust their mixing technique based on the moisture content of the sand, the ambient temperature, even the humidity. That kind of adaptive judgment develops through years of apprenticeship. Smith watched Kelleher's workers more carefully, and he had to admit that Weiss was correct about their skill. The lead mixer was indeed adjusting his technique constantly, adding water more slowly when the morning humidity was high, mixing longer when the cement appeared to be setting too quickly. But Smith also saw something else that the professor seemed to overlook. The quality of each batch varied significantly depending on which worker was mixing it. The experienced men produced consistently strong concrete, while the newer workers created batches that ranged from acceptable to problematic. Professor, what if we could eliminate that human variability? Smith asked. What if a machine could perform the same mixing action every time, with precise control over speed, timing, and ingredient ratios? Then you would have consistent mediocrity instead of occasional excellence, Weiss replied firmly. Machines cannot think, Mr. Smith. They cannot adjust for the subtle differences that separate adequate concrete from superior concrete. This is why European construction projects employ master craftsmen rather than mechanical devices. Kelleher nodded in agreement. The professor's right about one thing. Concrete quality is about reading the mix. I can tell by sight and touch whether a batch is going to cure properly. My best mixers can do the same. That's not something you can build into a machine. Smith thanked both men and walked away from the construction site, but his mind was racing with possibilities. The European approach treated concrete mixing as an irreplaceable craft skill, something that required human intuition and years of experience. But Smith saw the problem differently. Human variability wasn't a feature, it was a limitation. What if a machine could perform the same mixing action with mathematical precision, maintaining exactly 180 revolutions per minute for exactly the right duration, adding water at precisely the correct rate regardless of weather conditions or worker fatigue? That evening, Smith returned to his Milwaukee workshop with pages of notes and calculations. The challenge wasn't just mechanical, it was economic. At $8.50 per cubic yard, concrete remained too expensive for the ambitious construction projects that American cities needed. But if mechanical mixing could reduce costs to $3.20 per cubic yard while producing uniform 3,000 pounds per square inch strength concrete, it would revolutionize American construction. Smith lit the oil lamps in his workshop and began sketching his first design. A rotating drum with carefully angled blades, gear ratios calculated to maintain consistent mixing speed, and a system for adding materials in precise sequences. The European experts might believe that machines couldn't replace craftsmen's judgment. But Smith was convinced that American engineering could build something better than human inconsistency. The question wasn't whether it was theoretically possible. The question was whether he could make it work in the harsh reality of construction sites, where failure meant not just professional embarrassment, but financial ruin for everyone involved. The disaster that would teach Smith everything he needed to know about mechanical concrete mixing began at 7:32 on a Tuesday morning in October of 1900. His first prototype mixer sat silent on the Chicago construction site, surrounded by lumpy, unusable concrete that had cost him $47,000 in canceled contracts and nearly destroyed his reputation permanently. Smith crouched beside one of the failed concrete samples, pressing his thumb into the surface. The material crumbled under minimal pressure, barely 1,840 pounds per square inch strength instead of the promised 3,000. The Chicago Tribune had already run their headline, "Milwaukee Mixer Makes Mush." Professional humiliation was expensive, but the engineering lessons hidden in this failure would prove invaluable. Back in his Milwaukee workshop 3 weeks later, Smith spread out dozens of concrete samples on his workbench. Each piece told a specific story about what had gone wrong. Some samples showed obvious segregation. The heavy aggregate had settled while the cement paste floated to the surface. Others revealed incomplete mixing with dry pockets of cement that had never been properly wetted. The worst samples displayed the telltale signs of overmixing. Concrete that had been beaten into a soupy consistency that would never achieve proper strength. Smith opened his field notebook and reviewed the data he had collected during the failed demonstration. His machine had operated at varying speeds between 90 and 220 revolutions per minute, depending on the load and the engine's inconsistent power delivery. Hand mixing crews, he had observed, maintained blade speeds between 140 and 280 revolutions per minute, but their technique varied dramatically between workers and throughout each mixing cycle. The breakthrough came when Smith realized he had been solving the wrong problem. He had focused on building a machine that could mix concrete, when he should have been building a machine that could mix concrete correctly. The difference was mathematical precision versus mechanical approximation. Smith began by calculating the optimal mixing speed based on the physics of concrete chemistry. Portland cement required specific agitation to achieve proper hydration, enough motion to ensure complete wetting of cement particles, but not so much that the mixture separated or developed excess air bubbles. After weeks of testing, he determined that 180 revolutions per minute provided the ideal balance. Not 179, not 181, but exactly 180. The engineering challenge was maintaining that precise speed regardless of load variations, engine power fluctuations, or operator inexperience. Smith's original gear train had used a simple 2-to-1 reduction ratio, which provided adequate power but allowed significant speed variations. His new design employed a 3.7-to-1 reduction with a heavy cast iron flywheel that stored rotational energy and smoothed out power irregularities. But speed consistency was only part of the solution. Smith's analysis of the failed concrete samples revealed that blade design was equally critical. His original mixer had used flat steel blades that pushed material around the drum without creating the folding action that properly distributed ingredients. Studying slow-motion observations of skilled hand mixers, Smith noticed that the best workers used a specific scooping and folding technique that lifted material from the bottom of the mixing board and folded it over the top in a continuous spiral pattern. Smith redesigned his mixer blades to replicate this motion mechanically. Instead of flat pushing surfaces, he created curved blades angled at 27 degrees that lifted concrete ingredients up one side of the rotating drum and folded them over in a cascading action. The blade geometry was calculated to ensure that every portion of the mixture completed the full folding cycle exactly 12 times during the optimal mixing period. Material selection became another crucial factor. His original blades had been made from standard cast iron, which wore quickly and contaminated the concrete with metal particles. Smith replaced them with manganese steel, a material 4 times more wear-resistant than iron and chemically inert in concrete applications. The increased cost was significant, but the improved durability and concrete quality justified the expense. Testing the redesigned mixer required systematic comparison with hand-mixed concrete. Smith established a controlled testing protocol using identical materials, environmental conditions, and timing. His new machine produced concrete samples averaging 2,950 pounds per square inch strength with 98% batch-to-batch consistency. Hand-mixed samples from the same materials ranged from 2,100 to 3,200 pounds per square inch, with an average consistency variation of 23%. The mathematics were compelling, but Smith knew that construction contractors would demand proof under real working conditions. He arranged for a side-by-side demonstration at a Milwaukee brewery project where his mixer would compete directly against James Keller's most experienced crew. The test began at sunrise on a cold November morning. Keller's 6-man crew established their familiar rhythm immediately. Sand, cement, stone, water, mix for 12 minutes, pour, repeat. Smith's machine operator, trained specifically on the new mixing protocol, began his first batch at exactly the same time. The initial results favored the hand mixing crew. Their first batch achieved proper consistency in 11 minutes and produced strong, workable concrete. Smith's machine required the full 14-minute cycle that his calculations had specified, and the concrete appeared slightly stiffer than the hand-mixed batch. But as the day progressed, the advantages of mechanical consistency became apparent. Keller's crew began showing fatigue by mid-morning. Their mixing times increased to 13 then 15 minutes per batch. The quality of their concrete varied as tired workers made small errors in water ratios and mixing duration. 2 batches had to be discarded as unusable. Smith's machine maintained exactly the same performance throughout the entire day. Every batch required precisely 14 minutes. Every batch achieved identical consistency and strength. By afternoon, the mechanical mixer was producing batches faster than the hand crew, and every sample met specifications without waste or rework. The final numbers told the complete story. Keller's crew had produced 85 cubic yards of concrete in 10 hours, with 4 batches rejected for quality problems. Smith's mixer had produced 340 cubic yards of concrete in the same time period, with 0 rejected batches and consistent strength testing 200 points higher than the hand-mixed average. More importantly, Smith had identified the engineering principles that would define successful mechanical mixing for the next 50 years. Precise speed control through proper gear ratios and flywheel stabilization. Blade geometry that replicated optimal hand-mixing technique. Material selection that prioritized durability over initial cost. And systematic timing that eliminated human variability while maintaining the chemical processes that created strong concrete. The Milwaukee Brewery project became Smith's proof of concept, but it was only the beginning. Converting an industry built on centuries of handcrafting tradition would require more than superior engineering. It would require overcoming the professional skepticism of contractors who had built their careers on skills that machines threatened to replace. The success at the Milwaukee Brewery project meant nothing to contractors who had never seen Smith's mixer work. Throughout the winter of 1900, Smith discovered that superior engineering was insufficient to overcome decades of professional skepticism. Construction foremen who had built their reputations on hand-mixing crews viewed mechanical mixers as expensive experiments that threatened both their workers' livelihoods and their own expertise. Smith's first sales calls in Chicago revealed the depth of industry resistance. Contractors listened politely to his technical presentations, examined his strength test results, and inevitably concluded that their current methods worked adequately. Why risk project delays and cost overruns on unproven machinery when experienced crews could deliver acceptable concrete using time-tested techniques? The breakthrough came when Smith realized he was asking contractors to make the wrong choice. Instead of demanding that they choose between proven methods and superior technology, he would eliminate their risk entirely. Smith developed a guarantee that no contractor could refuse. 30 days of free mixer operation with a complete money-back promise if the machine failed to deliver savings and improved quality. The first contractor to accept Smith's offer was Patrick McMurphy, who was building a grain elevator in Minneapolis. McMurphy had calculated that his project required 400 cubic yards of concrete over 6 weeks, exactly the type of medium-scale job where mechanical mixing advantages would be most apparent. If Smith's mixer failed, McMurphy would lose only the time required to mobilize a hand-mixing crew. If it succeeded, he would complete the project faster and cheaper than his original bid anticipated. Smith personally supervised the installation of his mixer on McMurphy's site in March of 1901. The machine arrived on a railroad flat car, requiring a steam crane to position it near the concrete placement area. Smith's operator spent 2 days training McMurphy's crew on proper operation, material loading sequences, and maintenance procedures. The results exceeded even Smith's expectations. McMurphy's project, originally scheduled for 6 weeks with hand mixing, was completed in 4 weeks and 2 days. The mechanical mixer produced concrete at a consistent rate of 28 cubic yards per day compared to 14 cubic yards per day from the hand crew McMurphy had planned to use. More importantly, Every batch met strength specifications without the quality variations that typically required expensive remedial work. McMurphy's cost analysis revealed the true economic impact of mechanical mixing. Labor costs dropped from $4.30 per cubic yard to $1.80 per cubic yard. Material waste, which averaged 15% with hand mixing, fell to less than 3%. The total project cost was 31% lower than McMurphy's original estimate, generating unexpected profit that more than compensated for the risks of trying new technology. Word of McMurphy's success spread through the tight network of Midwest contractors faster than Smith could have achieved through any advertising campaign. Contractors began calling Smith directly, asking about mixer availability and terms for trial installations. By summer of 1901, Smith had 23 mixers operating across Illinois, Wisconsin, and Minnesota. Each successful installation generated additional orders. Contractors who had initially been skeptical became enthusiastic advocates when they discovered that mechanical mixing delivered consistent advantages on every type of project. Foundation work, which required large volumes of concrete in short time periods, became significantly more profitable. Bridge construction, where concrete quality directly affected structural integrity, achieved new levels of reliability and strength consistency. Smith's order book reflected the growing momentum. In 1902, he sold 23 mixers. The following year, 89 Smith mixers were operating across the Midwest. Each machine generated an average cost savings of $4.30 per cubic yard compared to hand mixing, a 51% reduction that transformed project economics throughout the construction industry. The financial impact extended beyond individual contractors to the entire construction supply chain. Concrete suppliers could reduce their safety margins because mechanical mixing eliminated the quality variations that required extra material allowances. Project schedules became more predictable because concrete production no longer depended on crew availability and weather-related delays that affected hand-mixing operations. Architecture firms began designing larger, more ambitious projects because reliable mechanical mixing made higher-strength concrete economically feasible, but success also created new challenges that Smith had not anticipated. Increased demand strained his manufacturing capacity and revealed weaknesses in his supply chain. The manganese steel blades that were crucial to mixer performance required specialized metallurgy that only a few foundries could provide. Gear components manufactured to Smith's precise specifications needed quality control that many machine shops struggled to achieve consistently. Smith expanded his Milwaukee factory to meet growing demand, but he also implemented rigorous quality standards that sometimes created delivery delays. Every mixer component was individually tested before assembly. Completed mixers underwent 48 hours of continuous operation testing before shipping. These procedures increased manufacturing costs, but they ensured that every Smith mixer delivered the reliability that contractors expected. The most significant challenge was training operators and maintenance personnel. Mechanical mixing required different skills than hand mixing, and many construction crews struggled with the transition. Smith established a training program that taught proper operation, routine maintenance, and troubleshooting procedures. The investment in operator education proved essential. Properly trained crews achieved consistently better results and experienced fewer mechanical problems. By 1903, Smith mixers were producing concrete for some of the Midwest's most prestigious construction projects. The new Chicago post office used Smith mixers exclusively for its foundation work. 3 major railroad bridge projects specified mechanical mixing to ensure concrete quality and construction schedule reliability. A dozen grain elevators across the wheat belt were built using Smith mixers, taking advantage of the consistent strength and reduced construction time that mechanical mixing provided. Industry publications began recognizing mechanical mixing as a legitimate alternative to traditional hand methods. Engineering News published a comprehensive analysis of mixer performance that validated Smith's technical claims and recommended mechanical mixing for projects requiring more than 100 cubic yards of concrete. The American Society of Civil Engineers invited Smith to present his research at their annual conference, marking the first time mechanical mixing received formal recognition from the engineering establishment. But even as success mounted, Smith remained focused on continuous improvement. His field experience had revealed opportunities to enhance mixer performance, reduce maintenance requirements, and extend operating life. The bearing systems that supported the mixing drum represented the most critical reliability factor, a lesson that would soon be demonstrated in the most dramatic and costly way possible. The momentum that had carried Smith from skepticism to industry acceptance was about to encounter its greatest test, and the outcome would determine whether mechanical mixing represented a permanent advancement or merely a temporary experiment that would be abandoned when the first serious failure occurred. The telegram arrived at Smith's Milwaukee office at 11:47 on the morning of February 16, 1904. Mixer bearing failure. Marshall Fields. Building stop foundation compromised. Stop need immediate assistance. Stop ransom. Charles Ransom never sent telegrams unless the situation was catastrophic, and this one confirmed Smith's worst fears about the project that was supposed to establish his reputation in Chicago's most prestigious construction market. Smith caught the next train to Chicago, but he already knew what he would find. The Marshall Fields department store construction project represented everything that mechanical mixing was supposed to achieve: massive concrete requirements, demanding quality specifications, and a schedule that hand mixing could never meet. Ransom had specifically requested Smith's most advanced mixer for the foundation work, and Smith had personally supervised its installation 3 weeks earlier. The scene at the construction site was worse than Smith had anticipated. 127 cubic yards of defective concrete sat in hardened lumps around the foundation excavation, representing 12 hours of continuous mixing that had produced nothing usable. The mixer itself sat silent, its bearing assembly seized completely, with metal shavings scattered around the base of the machine. Ransom stood beside the ruined concrete with a group of project engineers, their faces showing the particular strain that comes from explaining expensive failures to demanding clients. "The bearing locked up at 6:15 this morning," Ransom explained as Smith examined the failed machinery. "We had been running continuous shifts for the past 4 days, trying to keep pace with the foundation schedule. Everything seemed normal until the mixer started making grinding noises, then it seized completely. The concrete in the drum hardened before we could get it out." Smith traced the failure systematically. The main bearing assembly, which supported the rotating drum, had been designed for normal intermittent operation, 8 hours per day with regular maintenance breaks. But the Marshall Fields project had demanded continuous 24-hour operation to meet Ransom's aggressive schedule. The bearing had accumulated 847 operating hours in just 3 weeks, approaching the total service life that Smith had specified for normal use. More critically, Smith discovered that the bearing had not received the daily lubrication that his operation manual specified. The construction crew, focused on meeting concrete production targets, had skipped routine maintenance procedures to avoid interrupting the mixing schedule. Without proper lubrication, the bronze bearing surfaces had overheated and seized against the steel shaft, destroying both components completely. The technical failure was serious enough, but the timing made it catastrophic. Marshall Fields was Chicago's most visible retail construction project, with newspaper coverage and industry attention that amplified every aspect of its progress. The concrete failure would be reported in trade publications throughout the construction industry, providing ammunition for every contractor who had been skeptical about mechanical mixing from the beginning. Within hours of Smith's arrival, the story had spread beyond the construction site. The Chicago Tribune's afternoon edition carried a detailed account of the mixer failure under the headline, "Mechanical Marvel Malfunctions at Major Project." The article quoted several unnamed construction industry sources who claimed that the failure proved that complex machinery could not be trusted for critical structural work. The financial consequences were immediate and severe. Smith Manufacturing's stock price, which had risen steadily as mixer orders increased, dropped 73% in 2 days of trading. Construction contractors who had been considering mechanical mixing canceled their orders or postponed their decisions pending investigation of the Marshall Fields failure. Within a week, Smith's order book had shrunk from 47 pending sales to 4 confirmed orders. Industry publications quickly picked up the story, and the coverage was uniformly negative. Engineering News published an editorial titled Proof That Machines Cannot Be Trusted with Structural Concrete that summarized the professional consensus about mechanical mixing. The article argued that the Marshall Field's failure demonstrated the fundamental weakness of mechanical systems, their inability to adapt to unexpected conditions or continue operating when maintenance was neglected. Professor Gustav Weiss, who had been monitoring American mechanical mixing developments from his position in the German engineering establishment, published a technical analysis that used the Marshall Field's failure to validate European skepticism about American innovation. His paper, widely circulated among engineering societies, concluded that mechanical mixing represented a dangerous departure from proven craftsmanship methods that inevitably results in structural failures when complex machinery exceeds its design limitations. Smith faced the most serious crisis of his career, but he also recognized an opportunity that his critics could not see. The Marshall Field's failure had revealed specific weaknesses in his design that could be corrected through better engineering. More importantly, it had demonstrated the consequences of inadequate maintenance, lessons that would make his next generation of mixers more reliable rather than less trustworthy. Working 18-hour days in his Milwaukee workshop, Smith began redesigning the bearing system that had failed so catastrophically. The original design had used bronze bushings pressed directly into the cast iron frame, a configuration that required precise alignment and frequent lubrication. Smith's new approach employed replaceable bearing cartridges with built-in grease fittings that could be serviced without stopping the mixer operation. The redesigned bearing system incorporated multiple redundancies that prevented single-point failures. Instead of one large bearing supporting the entire drum weight, Smith distributed the load across 4 smaller bearings, each capable of handling the full operational load temporarily if others failed. The bearing cartridges could be replaced individually during routine maintenance, eliminating the catastrophic failures that had destroyed the Marshall Field's mixer. Smith also recognized that the original failure had been caused as much by operational procedures as by mechanical design. His new mixers would include automatic lubrication systems that eliminated dependence on operator maintenance. Grease reservoirs and distribution lines would ensure continuous bearing lubrication during operation, while warning systems would alert operators before lubrication supplies were exhausted. But the most important lesson from the Marshall Field's disaster was about durability versus initial cost. Smith's original bearing design had been optimized for minimum manufacturing expense, using materials and tolerances that met basic performance requirements. The replacement design prioritized longevity over economy, employing premium materials and precision manufacturing that would ensure reliable operation under the demanding conditions that major construction projects required. The new bearing system increased manufacturing costs by 37%, but Smith calculated that the improved reliability would reduce total ownership costs through decreased maintenance and eliminated downtime. More importantly, the enhanced durability would restore confidence in mechanical mixing by eliminating the catastrophic failures that had undermined contractor acceptance. As Smith worked on the technical solutions, he also developed a strategy for rebuilding industry confidence. Rather than hiding from the Marshall Field's failure, he would use it as proof that American engineering could learn from mistakes and emerge stronger. The next test of mechanical mixing would demonstrate not just superior performance, but the resilience and reliability that major construction projects demanded. The opportunity for that demonstration was already taking shape in California, where a natural disaster would create construction demands that only mechanical mixing could possibly meet. The earthquake that struck San Francisco at 5:12 on the morning of April 18, 1906, created the construction emergency that would vindicate everything Smith had learned from the Marshall Field's disaster. Within hours of the initial shock, fires were consuming entire city blocks while emergency crews struggled to establish safe zones and plan for massive reconstruction efforts. The scale of destruction demanded concrete production at levels that hand mixing could never achieve, and city officials were desperate enough to try any technology that promised faster rebuilding. Smith received the telegram from San Francisco's emergency construction coordinator 3 days after the earthquake. Need maximum concrete production for emergency rebuilding. Stop, can you provide mixers immediately? Stop conventional methods, insufficient for reconstruction. Scale, stop, Davidson. The message represented both an enormous opportunity and the ultimate test of whether his redesigned mixers could perform under the most demanding conditions possible. Smith's response was swift and comprehensive. Within a week, he had loaded 47 mixers onto railroad cars bound for California, along with replacement parts, maintenance equipment, and his most experienced operators. The shipment represented nearly his entire available inventory, but Smith recognized that successful performance in San Francisco would restore confidence in mechanical mixing more effectively than years of conventional sales efforts. The reconstruction challenge exceeded anything American construction had previously attempted. Emergency planners calculated that rebuilding San Francisco's commercial district would require 12,000 cubic yards of concrete daily for at least 6 months. Hand-mixing crews, even working around the clock, could produce perhaps 3,000 cubic yards per day. The mathematics were inescapable. Mechanical mixing was not just advantageous for the reconstruction effort, it was absolutely essential. Smith personally supervised the installation of his mixers throughout the city's reconstruction zones. The new bearing design, developed in response to the Marshall Field's failure, proved ideal for continuous emergency operations. Automatic lubrication systems eliminated the maintenance oversights that had caused the Chicago disaster, while the distributed bearing load design prevented single-point failures even under 24-hour operation schedules. The performance exceeded Smith's most optimistic projections. His 47 mixers produced an average of 12,000 cubic yards of concrete daily, matching the reconstruction planner's requirements exactly. More importantly, the concrete quality remained consistent despite the chaotic conditions and inexperienced operators that emergency construction demanded. Strength tests averaged 3,100 pounds per square inch, with less than 5% variation between batches. The real validation came not from production statistics, but from structural performance. San Francisco's reconstruction occurred while aftershocks continued to shake the region, providing a natural stress test for the concrete foundations being poured with Smith's mixers. Buildings constructed using mechanical mixing demonstrated superior resistance to seismic forces compared to structures built with hand-mixed concrete during the initial reconstruction phase. Engineering investigations revealed why Smith's concrete performed better under earthquake conditions. The consistent mixing achieved uniform material distribution throughout each batch, eliminating the weak spots that typically occurred in hand-mixed concrete. More importantly, the precise water-cement ratios maintained by mechanical mixing produced concrete with higher tensile strength and better crack resistance than the variable mixtures that hand mixing inevitably created. Professor Frederick Turnor, who had been monitoring mechanical mixing developments with academic interest, arrived in San Francisco to study the reconstruction project firsthand. His systematic testing of Smith's concrete samples provided the scientific validation that the engineering establishment required. Turnor's published research confirmed that mechanical mixing produced concrete with superior strength consistency, reduced permeability, and better long-term durability than conventional hand-mixing methods. The American Society of Civil Engineers, which had previously maintained cautious skepticism about mechanical mixing, issued a formal endorsement based on the San Francisco reconstruction results. Their technical committee concluded that mechanical mixing represented superior standard practice for projects requiring consistent concrete quality and high production rates. The endorsement effectively eliminated professional resistance to mechanical mixing and established Smith's technology as accepted engineering practice. Industry recognition translated immediately into commercial success. Construction contractors throughout the West Coast began ordering Smith mixers for their post-earthquake projects. By December of 1906, Smith had received orders for 138 additional mixers, representing more sales in 8 months than he had achieved in the previous 3 years combined. The financial recovery was equally dramatic. Smith Manufacturing's stock price, which had collapsed after the Marshall Field's disaster, reached new highs as investors recognized the company's dominant position in a rapidly expanding market. The redesigned mixers, which had initially increased manufacturing costs, now commanded premium prices because contractors understood their superior reliability and performance. More importantly, the San Francisco success established mechanical mixing as the foundation technology for American construction expansion. The concrete cost reductions that Smith's mixers achieved, from $8.50 per cubic yard to $2.95 per cubic yard, made large-scale construction projects economically feasible throughout the rapidly growing American cities. By 1910, 2,847 Smith mixers were operating nationwide, transforming American construction practices fundamentally. The skyscraper boom that defined early 20th century urban development became possible only because mechanical mixing provided the reliable, high-strength concrete that tall buildings required. Bridge construction, dam projects, and industrial facilities all benefited from the consistent quality and economic advantages that mechanical mixing delivered. The legacy of Smith's innovation extended far beyond immediate commercial success. The bearing design principles developed in response to the Marshall Field's failure became industry standards that remained unchanged through the 1950s. Heavy-duty ring gear drives, distributed bearing loads, and automatic lubrication systems defined reliable mixer construction for decades, proving that American engineers had learned to build equipment that lasted rather than equipment that merely functioned. The irony was not lost on Smith that the disaster which had nearly destroyed his company ultimately provided the foundation for its greatest success. The Marshall Field's bearing failure had forced him to confront the difference between adequate engineering and excellent engineering, between meeting specifications and exceeding expectations. The redesigned mixers that emerged from that crisis embodied the American industrial philosophy that building things right the first time costs less than fixing them forever. European critics who had dismissed American mechanical mixing as inferior to traditional craftsmanship found themselves studying Smith's designs and adopting his innovations. The Milwaukee mixer that couldn't work had become the global standard for concrete production, proof that American engineering ingenuity could transform entire industries when guided by the principle that machines should exceed human capabilities rather than merely replicate them. The concrete foundation beneath every American skyscraper built between 1910 and 1950 bore testimony to Smith's persistence in solving what European experts had declared impossible, and his wisdom in learning that the greatest engineering challenges often reveal themselves only after the first catastrophic failure.